Namaste, welcome to Pythagoras Academy. This is VIKRAM DACHEPALY. In this video, I am going to discuss a very interesting problem of finding Coulomb's force of interaction between two charges when a dielectric slab is inserted between them. And this is really challenging, but I'll make it very simple for you. Let us first try to understand the Coulomb's force between two charges in a dielectric medium so that we can get into the problem. And what is a dielectric medium in the first place? Any insulator medium is known as dielectric medium. Any medium in which there are no free charges to move, charges are tightly bound to their respective nucleus, that medium is known as a dielectric medium. For example, if you take a dielectric slab, there are positive and negative charges, but they are not free to move as compared to conductors. In conductors, the charges are free to move. When this dielectric material is subjected to external electric field E, the charges inside the dielectric medium will experience force, but they cannot move. All that will happen is the charges will slightly shift from their equilibrium positions, which will cause polarization. For example, in this case, negative charges experiencing electric force in the opposite direction, if they slightly shift, there is positive charge concentration on the right side and negative charge concentration on the left side. This is known as polarization. And when a dielectric substance is polarized, an internal electric field, EI, is created. So this is a dielectric medium. Vacuum is a perfect insulator, but any practical insulator will have charges, and any practical insulator, when subjected to external electric field, will undergo polarization. Now let us see what happens to the force of interaction between two charges in any dielectric medium. For example, consider two charges Q1 and Q2 separated by a distance r, and the medium in which they are placed is vacuum. This is the ideal case. And the Coulomb's force of interaction between them is given by Coulomb's law, that is 1 by 4 pi epsilon naught times Q1 Q2 by r square. The force is proportional to the product of charges and inversely proportional to the square of distance between them. And epsilon naught is known as the permittivity of free space or vacuum. And this electric constant 1 by 4 pi epsilon naught is dependent on the medium. Force between two charges is different in different media. It all depends on the extent in which that particular insulator medium can get polarized. So there is a constant, there is a physical quantity to define or to describe to what extent an insulator medium can get polarized. That is known as the dielectric constant of the medium. For example, if these two charges are placed in a dielectric medium at the same separation R, now force in the medium Fm is given by 1 by 4 pi epsilon m, permittivity of that particular medium, into Q1 Q2 by r square. And force in any medium due to the polarization of the medium will be lesser than the force in vacuum, and the force is decreased by a factor k. For example, force in medium m is force in vacuum by k, it is decreased by k times. So this k is known as dielectric constant of that particular medium. Greater is the dielectric constant of the medium, greater will be the polarization, and lesser will be the force of interaction between the charges in the medium. Now comparing these two equations, so force in vacuum is nothing but 1 by 4 pi epsilon naught, and you have k here, and Q1 Q2 by r square. So epsilon m is nothing but k times epsilon naught. The dielectric constant k can also be defined as the relative permittivity of the medium, divided by the permittivity of the vacuum. So now observe this equation. Force in the medium Fm can be rewritten as 1 by 4 pi epsilon naught Q1 Q2 divided by K R square. I'll express this as under root K R whole square. Carefully observe this equation. 1 by 4 pi epsilon naught Q1 Q2 by root K R whole square. This gives us an understanding that when two charges are separated by distance r in any medium of dielectric constant K, it is equivalent to two charges separated by a distance of root kr in vacuum. So this is a very important concept to solve the problem which I mentioned in the beginning of the video. The distance r in a medium is equivalent to a distance of root kr in vacuum. So now let us get into the problem. Say there are two charges, Q1 and Q2, separated by a distance r, and a dielectric slab of dielectric constant K and thickness T is inserted between them. Now what is the force of interaction between them? If the entire medium is dielectric medium, this is the force 1 by 4 pi K epsilon naught Q1 Q2 by R square. Or if the entire medium is vacuum, it is 1 by 4 pi epsilon naught Q1 Q2 by R square. Now there is a dielectric slab which is inserted between two charges. How do we deal with this? We are going to apply this concept. A distance r in any medium is equivalent to a distance of root kr in vacuum. So I'll convert this problem into two charges Q1 and Q2 separated by a distance, effective distance of r dash in vacuum, so that the force between them can be easily expressed as 1 by 4 pi epsilon naught Q1 Q2 by r dash whole square. But what is r dash? That is the effective distance in vacuum. So how do I get this r dash? This r dash is nothing but, so r minus t length is already in vacuum, r minus t length is already in vacuum, plus t length in dielectric medium is equivalent to root kt as we just derived. R length is equivalent to root kr, so t length is equivalent to root kt. So r dash is r minus t of vacuum plus root kt of vacuum. That is the effective distance in vacuum between two charges Q1 and Q2. The problem is pretty much simplified. The force of interaction between them is 1 by 4 pi epsilon naught Q1 Q2 by, so r dash is r plus t times root k minus 1. So I'll write this here, r plus t times under root k minus 1 whole square. That's all. This is the force of interaction between two charges when a dielectric slab is inserted between the charges. As simple as this. If you have any questions or suggestions, you can always use the comment section to interact with me. I'll be more than happy to help you out. This is VIKRAM DACHEPALY signing off. Namaste.